I will go ahead and have to let y'all know that I will be looking at my phone for this presentation because there's absolutely no way I'm remembering everything I have to say on here. Hey everybody, and welcome to the show. My name is Ottoson. And today we are going to be diving into something you might not think about every day, but something we all use constantly, whether we realize it or not: maps. And more importantly, we're going to be talking about the invisible engine behind them: geometry. Whether you're navigating a road trip with Google Maps, following a hiking trail with a printed topographic map, or studying geography in school, maps are built on math, especially geometry. So how does this math help us sense out the real world? And how do cartographers, the artists and scientists behind maps, turn the shape of our planet into something flat, readable, and useful? Let's start with one of the most fundamental problems in map making. The Earth is a sphere, but maps are flat. How do you take something round and represent it on a flat surface without distorting it? This is where geometry projections come in. Mathematical methods for transforming the curved surface of Earth into a two-dimensional image. Imagine peeling an orange and trying to lay the peel flat. It won't be perfect. That's the challenge cartographers face. Some of the most well-known map projections include the Mercator project, developed in 1569. This project preserves angles and shapes fairly well, which is why it is great for navigation. But it distorts size, making regions like Greenland look much larger than they are. The Robinson project. This one aims to balance shape and size, creating a visually appealing map. Good for world maps where no single property is perfect, but everything is close enough. Each projection involves careful geometric decisions about what to preserve: area, angle, shape, or distance. But no projection can preserve all four. Each projection involves careful geometric decisions and whether preserve. I just said that anyways. Next up, we're going to be talking about coordinates, the geometric backbone of every map. Every location on Earth can be described using two numbers: latitude and longitude. These form a grid system over the globe, kind of like X and Y coordinates in algebra. Latitude lines run horizontally and measure how far north or south you are from the equator. Longitude lines run vertically and measure how far east or west you are from the prime Mediterranean. Anyways, these coordinates are measured in degrees, and they help us locate any point on Earth, from New York to Nairobi, and from the Eiffel Tower to your favorite coffee shop. This system allows GPS satellites to pinpoint your location to within a few feet, all thanks to geometry. Let's take a step back in time. Before GPSs, before satellites, before drones, how did people measure land accurately? Either triangulation, a classic method used for, you guessed it, triangles. Surveyors would measure one known baseline distance, then use a compass or angled measure device, like a theodolite, to calculate other distances by forming triangles. Once they know two angles and one side, they solve the rest using trigonometry, a branch of geometry. Triangulation was essential for creating topographic maps, measuring national borders and laying out cities long before Google Earth. Let's say a map says 1 inch equals 1 mile. What does that mean? That's a scale, a geometric ratio that tells you the distance of the map compared to real life. If you walk 2 inches on the map, that's 2 real miles. This is crucial for accurate navigation, planning, and measurement. Without a reliable scale, distances could be completely off and you could end up miles from your destination. Choosing the right scale also depends on the map purpose. A city map might use a large scale, like, for detail, while a world map uses a small scale, like 50 million, to fit everything in. When you look at a map, you see more than lines and labels. You see features, rivers, roads, borders, coastlines, and more. These are all represented using geometric elements. Lines to represent roads, highways, and borders, curves for rivers and elevation contours, and polygons to define lakes, parks, or entire countries. Cartographic simply real-world features into geometric shapes that are easy to understand at all glance, a process known as generalization. It is all about clarity and function. A map isn't just about data, it's also about design. That's where geometric principles like symmetry, alignment, spacing, and come into play. Good cartographers use layout techniques to make maps not only accurate but readable and visually pleasing. Ever notice how map labels never overlap, or how symbols are evenly spaced? That's intentional, and it's based on graphic geometry and visually balanced. A well-designed map tells a story, clearly and efficiently. Modern maps have gone digital, and they rely on advanced geometry more than ever. GPS, also known or short for Global Positioning System, uses satellites and geometry to triangulate your position in real time. GIS, which is also short for Geographic Information System, allows us to layer, analyze, and visualize spatial data like population density, land use, or disaster zones. Both systems rely on coordinate geometry, vectors, and spatial algorithms to calculate decisions, directions, and changes over time. It's geometry in motion. Maps aren't just flat, they can also show elevation or the third dimension. Topographic maps use contour lines, which are curved lines that connect points or equal elevation. These lines are a geometric way to show hills, valleys, and slopes, so hikers, engineers, and developers can read the terrain in 2D. Navigation 2 and geometric, a compass measure directions in degrees, from 0 north through 360 navigators using bearings and angles to plot routes, whether on land, sea, or air. And in urban planning, cities are often laid out on a grid system. Roads intersect at right angles. Blocks form rectangles, and zoning maps use geometric boundaries. From traffic flow to utility lines, geometry helps design efficient, livable spaces. So what's the takeaway? Geometry is the unsung hero of cartography. It helps us project our round Earths on flat maps, pinpoint any place with latitude and longitude, measure land and calculate distance, represent national and human-made features, design maps that are not just accurate, but beautiful, and powers technologies like GPS, GIS, and smart cities. Without geometry, maps would be misleading, confusing, and imprecise. But with it, we get tools that help us understand the world, navigate it, and plan for the future. Thanks for joining me on this journey of geometry. This is Ace signing out.